So we're not quite done with the alpha carbon attack using halogenation. We looked at some examples in the previous video. We talked about the differences between the acidic and the basic conditions, and we said that under acidic conditions, we actually see that the alpha hydrogen, only one of them gets replaced by a halogen, such as chlorine or bromine. And then in basic conditions, we discussed the option that all of the alpha hydrogens are going to be replaced by bromine or chlorine. So we need to take a few moments and look at the mechanism to really figure out why these differences begin to happen. Because without the mechanism story, we're probably not going to understand what's going on with this molecule at the molecular level. Okay, so let's first start off with acidic conditions, and let's just randomly pick a carbonyl. Again, this could happen with ketones or it could happen with aldehydes. It really doesn't matter. So we'll do a methyl group here, and then we'll do CH2 and CH3 group there. We're only going to keep it simple, so we're only going to focus on one of these hydrogens with the mechanism itself. So if I take a look at this ketone, I'm just going to erase that CH2 and draw one of these hydrogens pointed straight down, because I know that this mechanism route is going to discuss the removal of the alpha hydrogen. So I just want to expose the alpha hydrogen a little bit, so that way on a sheet of paper I can draw this mechanism a little bit more smoothly. Okay, so we've got this ketone in this case, and let's just change this methyl group to a hydrogen. Again, just to keep it simple, because we are focused just simply on the mechanism, and that's it. And we are throwing this into acidic conditions. So we're going to start off with a acid mechanism first. So we're looking at H plus. Well, I know H plus is just not hydrogen, right? I know that most of the time with H plus, what I really mean is protonated water. This is going to be a oxygen that carries with it 3 bonds, and it probably has a free set of electrons on it. So this is carrying a positive charge for me, and that's really the H plus. That's really what we describe as the acid. It always has been. That story has never changed. So we know that this protonated water, it's not neutral. It wants to be neutral, and it can be neutral if it can give up a hydrogen. It needs to cleave one of these bonds, right? And if it can cleave one of these bonds, for instance, let's say that hydrogen there, then this can revert back to water, and this is a proton donor, and that's the definition of the acid. Okay, so what's in this molecule as far as the organic goes that will take that hydrogen? That's the question that we have to answer. Well, these things never really change. I mean, we get a slight positive and a slight negative charge in that molecule. So if I want to start off with the mechanism route, and I look at this hydrogen, and I know that this hydrogen has to go away, and now I have to find it a home in the molecule, and I figure out where this hydrogen is going to go, it's probably going to go to the negative end of the molecule. So that's going to be at the oxygen, right? Those laws, those kind of rules, they never change. So I need to show that mechanism. So curvy arrow mechanism always starts at the negative end. It points to the more positive piece, so it's going to grab that hydrogen and pull it off, and that allows the electrons here in this bond to basically be given to oxygen. And now what we do is that we form this CH3, CH, and again, really remember, I'm just writing the hydrogen down below. That way it shows up a little bit better on the sheet of paper for me when I do the mechanism. And this thing now gets a hydrogen. Okay, well, if that gets a hydrogen, this oxygen now has 3 bonds. That turns it into a positive charge like we've seen before in the past, and we know that this thing is not going to be very stable. We know it's going to actively search to get rid of that positive charge if it can, and there's a couple of options for it here. One of those options that this mechanism will focus on is look at what we have just made. We have ripped a proton off and we have ended up with water again. So water is actually still in solution, and that water is going to carry with it some free pairs of electrons. So again, this is kind of negative, right? And it's going to look for something positive in the molecule. Well, you're probably going to start off looking up here and say, well, that's my positive piece. Well, it is. That is true. That is your positive piece. However, that's not the only site of attack. That's what this lecture is all about, right? It's about the reactions that can happen at the alpha carbon. So we want to focus in on this alpha carbon, and we want to take a look at what goes on at this alpha carbon. So this next step, there is a possibility that this water molecule can look at this hydrogen and pull that acidic hydrogen off of this organic. And you're probably questioning, well, why? Why would it choose that proton and pull it off? Why is that proton acidic? And the reason is because if this hydrogen can leave, then the electrons that are involved in this C to H bond can be shifted here. And then if those shift there, this carbon's got to make the decision to shift those electrons up, and we end up now without a protonated oxygen there. So CH3, this has lost a hydrogen. We formed a double bond now to this carbon that now has an OH group up here at the top instead of a C double bond O, and then a hydrogen there. Notice what we have formed here. This is our unstable enol structure, right? So the enol structure, once again, ene for double bond and ol for alcohol. So there it is. So we know that this will rearrange if it can. Okay, well the problem here is that we don't want to give it time to rearrange. So what we've added into this solution, remember, we're halogenating it, so there's a halogen involved. Well, that halogen, let's pretend, is bromine, Br2. So Br and Br, right? So we've talked about this double bond reaction with Br2 and DCM a little earlier on in the course, and we've also talked about the addition of bromine with something like water that can do it as well. So that mechanism is going to be coming back. You have to understand that these electrons are in constant movement. London dispersion forces can happen. One of these bromines could become slightly positive, and if one of those bromines become slightly positive, well, what we can see is that this bromine can be attracted to one of these carbons involved in the double bond. So we know that this will want to rearrange. This enol is very uncomfortable. It doesn't like it. So it's going to want to take some of its electrons back, and it's going to kind of shove them down onto carbon again. And carbon says, okay, well fine, if I'm going to do that, and if I have to take your bond back, oxygen, I need to get rid of the double bond that I just formed. So what's going to take care of the double bond? Well, that's one of the bromines. So bromine will come and break the bond, really, and then one of those bromines will add on to the molecule, and the other bromine basically gets swept out of solution. So now our product, after this enol rearrangement, basically, due to that unstable enol, is something that looks like CH3, CH, with a bromine hanging off at this location, carbon double bond OH, because it hasn't lost that proton yet, right? We haven't shown that proton go away. So that's the result of this enol rearrangement that forms. Okay, well, we have to make this oxygen happy. So it's kind of reverted back on itself. It's made the C double bond O again in a way, but we need something to pull that hydrogen off so that way we can get rid of the charge on the oxygen. And that's nothing more than just water that's swimming around in solution, right? If water can pull off this acidic hydrogen, why can't it pull off this acidic hydrogen? And it can. So water can come around, take a hold of this hydrogen and pull it off, and the electrons in that bond basically are moved to the oxygen, and what we have now is a CH3 group, a CHBr, a C double bond O, and a H. And that's the formation of this halogenated organic. So overall reaction, the overall reaction would look something like CH3, CH2, carbon double bond OH plus Br2 and a little bit of acid. And the resulting product of that is a alpha hydrogen getting removed and a bromine going on in its place. So this is our product. So if we want to understand how that product is basically made, this is the mechanism route on which that product is made. So here we have the aldehyde, the double bond with the oxygen pulls the hydrogen off, forms water. That gives me a protonated alcohol in a way. Well, this will rearrange to kind of take care of that positive oxygen. So water will pull the alpha hydrogen off, a double bond forms between the two carbons, and the electrons get shoved up. This makes an enol. The enol is not stable. It will rearrange on itself, and oxygen will try to push the electrons back down, forcing the carbon to break the double bond. Bromine is in solution. That goes on to the carbon where the double bond breaks. We still have this leftover hydrogen that started this thing off in the very beginning. Water will pull that hydrogen back off, reforming our catalyst because we've now reformed our acid, and that ends up with the brominated organic that is our product. So that is the mechanism for the acid catalyzed halogenation reaction. So in the next video, we're going to look at how the basic conditions change things up a little bit, because once this goes forward, well, there's really nothing else left, right? Once this bromine goes on, well, you're looking at more alpha hydrogens. Well, there is an alpha hydrogen here, but is that thing really basic now? And the answer is no, it's not basic. It's going to be much harder to pull that hydrogen off because that bromine there is on the carbon. So we can't really pull another hydrogen off anymore. Bromine is the blocker, right? It's kind of the bully that's coming into the picture now and saying, I don't think so, you're not coming in and you're not pulling this hydrogen off anymore. That's not exactly what happens with the base catalyzed reaction that we'll see in the next video.